So now we're moving into Unit 16, boxes C and D here, and we want to talk about concavity and look at how you set up a concavity table to see what the concavity is of your function in various intervals here. So first off, what the heck is concavity? Well, for our purposes, concavity, we only have to look at two possible cases. Your curve can be concave up, okay, or it can be concave down. A curve that is concave up looks like this, okay? It's like that parabola you saw in grade 10 that opens up. Let's just say curve opens up, okay? And in this course, you can also have things that look kind of like this, or look kind of like this, okay? Those could be exponential functions that you've seen before, okay? As long as the curve kind of opens up or the slope of the tangent to the curve is increasing. Okay? If we take a look at, say, this one here, if I draw my slope like that, my tangent like that, and I draw it like that, I draw it like that, my tangent is getting, slope of my tangent is getting bigger and bigger and bigger. So the slope of the tangent is increasing where our curve is concave up. What does that mean? Well, if the slope of the tangent is increasing, okay, that means our first derivative is increasing. If our first derivative is increasing, then our second derivative has to be positive. Okay? Okay, just like we saw with intervals of increase and decrease. So if our first derivative is positive, if our second derivative is positive, we know that our curve is concave up. And we saw this already with our second derivative test. We apply the second derivative test. If it's greater than 0, we know that we had a local minimum, okay? So we did this sort of thing here. Second derivative is positive. We knew that our curve, we had a minimum, or our curve was concave up. Okay. Conversely, as you've no doubt guessed, we can have concave down. Concave down means that our curve opens down in the case of our parabola. Or we can have something that looks like that, or looks like this. And the slope of our tangent is always going to be decreasing, okay? We can start from something like 0 here, and it gets progressively smaller, smaller, and smaller. So we can say slope of the tangent is decreasing, okay, which of course tells us that our first derivative is decreasing. So our second derivative has to be less than 0 or negative. Okay? And again, just like in our second derivative test, second derivative is negative, tells us that our curve is concave down. Okay? Okay. So that's concavity. Now, when we're dealing with intervals of increase, we gave a special name to the points where our curve went from increasing to decreasing. We call these turning points, or local max and min. We also give a special name to the points where our curve goes from concave up or concave down to concave up. We call these points of inflection. Now, we've mentioned points of inflection before without really talking about what they are. But that's the definition of a point of of a point of inflection. It's a point on the curve, okay, and it has to be on the curve. Okay, so the function has to exist at that point, where the concavity changes. So what do they look like is we can have a curve that is concave up and then switches to concave down. Okay? So this is, I'll just say CU for concave up, CD for concave down. Or we could have the opposite. We can have a curve that is concave down. Let's see. Oh, wait. It is concave up, yeah. Or it could look something like that. Okay. Where we're also going concave up to concave down. Or of course it could go concave down to concave up. But each of these is a point of inflection. Now, what is true about points of inflections? Well, at a point of inflection, our second derivative is equal to 0, or it does not exist. Okay. So this suggests to us a possible way of finding points of inflections. Take our second derivative, set it equal to 0, or look for the points where it does not exist. Okay. Also, I'll just say points of inflection often occur at points where our first derivative is also equal to 0. Okay. So we encountered these when we were looking for critical numbers. Sometimes we had a local max, sometimes we had a local min. Other times we said that these things were points of inflection. Okay. So let's just take a look at an example of determining the points of inflection and determining the intervals where a function is concave up and concave down. So we've got a function here, f at x equals x over x squared plus 1. And if we're going to look at concavity, we're going to need our second derivative. So our first derivative, if you work it out, is 1 minus x squared over x squared plus 1 all squared. And our second derivative, if you work it out, is going to be negative 2x times 3 minus x squared all divided by x squared plus 1 cubed. And in a lot of practice questions for this unit, you'll be given the first derivative and the second derivative because we kind of assume that you already know how to do the differentiation and the factoring to put it in simplified form, because we've been working on that for a couple of units now. So let's set about trying to find our points of inflection here. And what we want to look for, remember, is where our second derivative equals 0, or our second derivative does not exist. And again, this is completely analogous to what we did with the first derivative when we were doing our intervals of increase and decrease. So points where the second derivative is going to equal to 0, we are going to set the numerator equal to 0. For points where it does not exist, we're going to set our denominator equal to 0. and we're going to solve for x. So our numerator first. Negative 2x times 3 minus x all squared, sorry, just squared, equals 0. And let's solve here. So we're going to have x equals 0. And we're going to have 3 minus x squared equals 0 from that term in the brackets, which gets us x squared equals 3, or x equals plus or minus root 3. Root 3 is about 1.73 here, just so we have some idea of the value. What about where our second derivative doesn't exist? Let's see. We've got our denominator is x squared plus 1 cubed. Let's set that equal to 0. Take the cube root of both sides. X squared plus 1 equals 0. Bring the 1 over to the other side. X squared equals negative 1. And can we solve this thing? Shaking our heads. Why not? Yeah, it'll be an imaginary number, and we're always working with real numbers in this course. Okay, so for us, we can just say no solution. To be mathematically correct about all of this, when I gave the question, I should say that the domain of the function is the element of real numbers. But I should have just said that at the very beginning of the course and then said that that applies to every function that we're going to run into. But yeah, no imaginary numbers. So we have no solution there. So we've got 3 possible points of inflection. Okay? And the way you check to see whether this is a point of inflection or not is you set up what's called the concavity table, using these to define our intervals. So I'll just say these things here will define our intervals. And we want to check the sign of our second derivative in each of these intervals. So our intervals are going to be negative infinity to negative root 3, negative root 3 to 0, 0 to positive root 3, and positive root 3 up to positive infinity. And we want to see how each term in our second derivative behaves. So we've got a negative 2x, we've got a 3 minus x squared, and we've got an x squared plus 1 cubed down in our denominator. And together, those will give us the sign of our second derivative. All right, are there any that are really easy to do here? Okay, what's that going to be? Negative 2x. Positive, positive, negative, negative. Right. So it's going to be the opposite of the sign of x. What about the third one here? X squared plus 1 all cubed. It's always positive, right? Because we're squaring it. Cubing it isn't going to change the sign. And we're always adding something there. It's the one in the middle that's a little bit tricky. So let's see. We can imagine putting in a test value of something like negative 10. We square it, we get 100, so it's 3 minus 100, so it'll be negative. Next column, we can imagine putting in like 1, negative 1, sorry. But we square it, we get positive 1, 3 minus positive 1, all right, positive. And then the same sort of thing there and there, positive and negative. So our second derivative is going to be negative, positive, negative, and positive. So what does this tell us about the concavity of our original function? Well, let's see. If our second derivative is negative, this is going to be concave down. If our second derivative is positive, concave up, concave down, and concave up. Okay? Now, we can look for our points of inflection, because a point of inflection is where our concavity changes. Okay? So we've got, let's see, 3 points of inflection here. Okay? And we'll just say point of inflection, point of inflection, point of inflection. Because at each of these places we switch from concave down to concave up, or concave up back to concave down. Okay. So we can read off what our x values are. Here our x value is -3. Here our x value is 0. Here our x value was, negative root 3 there, positive root 3 there. And we can sub those back into the original function to figure out our y values. We get negative root 3 over 4, 0, 0, and root 3 over 4. Okay. So 3 points of inflection on our curve here. Okay. All right. So what does this graph look like? It looks something like this. Our points of inflection, 0, 0, okay, because it's clearly concave down over here, concave up over here, and sort of right about here, and right about here. Actually, a little bit more. But over here, you can see it's concave down here, concave up as we get to larger and larger values of x. So those are our points of inflection. Okay. And sorry, one final note here. Actually, I'll do that on the next page, sorry. Note. Just because you find a point where the second derivative is equal to 0 doesn't mean that there has to be an inflection point there. Yeah, I'd say does not mean there must be an inflection point. It's just an indication that there's a possible inflection point there. Okay. So an example would be something like f at x equals x to the power of 4. We take our first derivative. We take our second derivative, okay, and we set it equal to 0. Where is our second derivative equal to 0? At x equals 0. But we know that the graph of this function looks kind of like this. X, y, this is f at x, okay? So even though the second derivative is 0, here at x equals 0, that point isn't a point of inflection. It's a regular old turning point or local minimum. Okay? So the way to check for sure if you've got an inflection point is to set up that concavity table. All right.